For many years we astronomers have looked towards our galactic neighbor Andromeda. It is a majestic spiral galaxy, much like our own Milky Way. We have observed it hurtling towards us. This observation led to a widely accepted prediction. Our Milky Way and Andromeda were destined for a spectacular collision. This cosmic event was projected to occur billions of years from now. It wasn't something for us to worry about in our lifetimes or even for many generations to come. But it painted a dramatic picture of our galaxy's far future, a grand cosmic ballet leading to transformation. The idea of this collision has captivated scientists and the public alike. Imagine two immense collections of stars, gas, and dust merging. Each galaxy contains hundreds of billions of stars. While individual stars are unlikely to collide directly due to the vast spaces between them, the gravitational forces at play would be monumental. The galaxies would distort each other, pulling out long streamers of stars and gas. This gravitational dance would irrevocably change their structures. The eventual outcome was envisioned as the birth of a new, even larger galaxy, often nicknamed Milkomeda. This future elliptical galaxy would be a testament to cosmic evolution. This prediction wasn't just a guess, it was based on solid observational data. Scientists measured Andromeda's speed and direction relative to us. The light from Andromeda shows a blue shift. This means it's moving towards us, as the wavelengths of its light are compressed. Early measurements confirm this approach at a speed of roughly 110 kilometers per second. That's incredibly fast, over 246,000 miles per hour. For decades, this blue shift was the primary indicator of the impending galactic encounter, shaping our understanding of the local group's dynamics and our own galaxy's ultimate fate. Further observations, especially from the Hubble Space Telescope, helped refine this picture. Scientists were able to measure Andromeda's sideways motion or proper motion. This was crucial. Knowing only the radial velocity, towards or away from us, isn't enough to predict a collision. A galaxy could be moving towards us but still pass by at a safe distance if its sideways motion is significant enough. However, the detailed measurements strongly suggested that Andromeda was indeed headed for a direct or near-direct hit, setting the stage for a galactic merger in about 4.5 billion years. This became the standard narrative in astrophysics. However, the universe often has surprises in store for us. Science is a journey of discovery, not a fixed set of facts. Just when we think we have a clear picture, new data can emerge. Recent developments, hinted at in breaking astronomical news as recently as yesterday, June 1, 2025, suggest a potential re-evaluation of this grand cosmic collision. Could it be that the Milky Way and Andromeda might not crash into each other after all? Or perhaps their encounter will be significantly different from what we've long anticipated. This is the exciting frontier of current astrophysical research. This potential shift in understanding is profound. It challenges a cornerstone of our local galactic forecast. The long-held scenario of a head-on collision leading to Milkomeda might need revision. Imagine telling someone the Earth isn't round after centuries of agreement. This is on a similar scale for galactic astronomy. These new whispers of a different destiny stem from incredibly precise measurements and sophisticated new simulations. The universe is always teaching us, and sometimes the lessons rewrite the textbooks. We must remain open to these new possibilities, however surprising they may be to our established views. The implications of such a revision are vast. If Andromeda is not on a direct collision course, its path might be a near miss, or a more glancing blow. This would dramatically alter the future evolution of both galaxies. The intense tidal disruptions and star formation bursts associated with a direct merger might be less severe or occur over a much longer timescale. The very structure of the future local group of galaxies would be different. This new perspective doesn't mean previous work was wrong, but rather that our tools and understanding are constantly improving, allowing for finer details to emerge. These emerging insights are prompting a flurry of activity in the astronomical community. Scientists are scrutinizing the new data and rerunning complex computer models. The question is no longer just the collision will happen, but it will happen in the way we thought. This is how science progresses. A bold prediction is made, tested rigorously, and sometimes overturned by even more precise observations. The story of the Milky Way and Andromeda is far from over. In fact, a new, unexpected chapter might just be beginning, compelling us to look again at our cosmic neighborhood. Understanding the paths of galaxies requires incredibly precise measurements. We need to know not just how fast a galaxy is moving towards or away from us, its radial velocity, but also its motion across our line of sight, its tangential or proper motion. Think of it like this. If a car is speeding towards you, you also need to know if it's aimed directly at you or if it will pass to your side. For galaxies billions upon billions of miles away, measuring this sideways drift is an immense challenge, yet it is this very measurement that is key to predicting their future interactions. The European Space Agency's Gaia mission has been a game-changer in this regard. Launched in 2013, Gaia is meticulously mapping the positions, distances and motions of over 1 billion stars in our Milky Way and nearby galaxies. Its precision is unprecedented. Gaia can measure the apparent shift in a star's position to an accuracy equivalent to measuring the width of a human hair from over 1,000 kilometers away. This incredible accuracy allows for much more refined calculations of Andromeda's proper motion by observing the collective movement of its stars against the backdrop of more distant objects. Earlier data from Hubble provided the first crucial estimates of Andromeda's tangential velocity. These were groundbreaking at the time and strongly supported the collision scenario. However, Gaia's subsequent data releases have provided an even sharper view. Even tiny adjustments in the measured tangential velocity, when projected over billions of years and vast cosmic distances, can lead to significantly different outcomes for the predicted encounter. It's possible that these latest, ultra-precise Gaia measurements, perhaps combined with new analytical techniques or more sophisticated simulations of gravitational interactions within the local group, are the source of this potential revision. These advanced tools and the data they provide are pushing the boundaries of astrophysics. They allow us to test our models of the universe with increasing rigor. If the Milky Way and Andromeda are indeed on a slightly different course than previously calculated, it would be a testament to the power of these technological marvels and the scientists who interpret their findings. It reminds us that our understanding of the cosmos is dynamic, constantly being refined by our ability to observe it with greater clarity and precision. The universe is a complex system, and our models must evolve with our capacity to measure it. If the latest findings, suggesting a different fate for the Milky Way and Andromeda, are confirmed, the ripple effects on our understanding of galactic dynamics will be significant. A near miss, rather than a direct merger, would imply different gravitational interactions. The exchange of material, the triggering of star formation, and the ultimate restructuring of both galaxies would follow a different script. This could mean that the eventual formation of a giant elliptical galaxy from their union might be delayed, or perhaps it might not happen in the same way at all, leading to a more complex, prolonged interaction. This potential revision also impacts our models of dark matter. Dark matter is the unseen substance that makes up the vast majority of mass in galaxies and galaxy clusters. Its distribution plays a crucial role in how galaxies interact gravitationally. The precise trajectory of Andromeda relative to the Milky Way is influenced by the gravitational pull of all the matter between and around them, including these vast dark matter halos. If their paths are different from what was predicted, it might mean our assumptions about the distribution or behavior of dark matter in the local group need refinement, offering new clues about this mysterious cosmic component. Furthermore, this evolving story underscores a fundamental truth about science. It is a process of continuous refinement and discovery. Long-held theories, even those supported by substantial evidence, can be revisited and revised as new data and more sophisticated tools become available. This is not a weakness of science, but its greatest strength. The willingness to question, to test, and to adapt our understanding in the face of new evidence is what drives progress. The potential adjustment to the Andromeda collision narrative is a perfect example of science in action, a dynamic interplay between observation, theory, and technological advancement. Looking ahead, astronomers will undoubtedly focus on gathering even more precise data and running more detailed simulations to clarify the future of our galactic neighborhood. Future Gaia data releases, along with observations from next-generation telescopes, both on the ground and in space, will provide crucial pieces of this cosmic puzzle. Whether our Milky Way is destined for a grand merger or a close cosmic dance with Andromeda, the journey to uncover that truth is a thrilling endeavor. It reminds us that the universe is full of surprises, and there is always more to learn about our place within it, keeping us humble and ever curious.